risk of predation did have an impact on the distribution of their prey. So as I mentioned, the highest concentrations of Adelie penguins and the risk of predation is much higher on this side of the bay, and the killer whale and minke whales tended to segregate more on this side. And here you can see the feeding locations of Adelie penguins that were based on the satellite data. How am I doing on time? Getting close here. So our preliminary conclusions are that the krill and fish were very abundant in this region. This was the most comprehensive study that's ever been done on this bay, in this southern end of the Ross Sea. They clearly make use of the fast ice, and they also actually go down to the seafloor, so they can sit on the seafloor feeding on phytodetritus and avoid diving predators as well. But on the other hand, the predators have adapted to this presence of a persistent food resource. The 3 Adelie penguin colonies are increasing on Ross Island. The population of killer whales is increasing, and there's been a very stable Weddell seal population for a number of years now. One of the results of the study that we did with the fast ice dynamics showed that over the last 30 years, the ice edge of the fast ice extent, the maximum fast ice extent, has not changed substantially over that time period. While during that same time period, the Ross Sea, the greater Ross Sea ice edge extent has actually increased. So the processes that are changing the Ross Sea ice edge haven't impacted the local dynamics at all. And so the location of that ice edge and the persistence of that ice edge as a stable platform and also a refuge for the prey affects the whole marine food web in this region. All right, I better stop there and let Chuanmin give his talk. Thank you. Oh, and to acknowledge all of the people that helped out, Heather Broadbent has been a critical member of both the Northern Gulf of Mexico and the Antarctic systems, and a variety of other students and staff.
We have time for 2 short questions. Am I?
Hendrik, what about I'm wondering about the role of the dispersant of the marine snow, and if you think that contributed
There's a group now, there's a new consortium that's been funded that's looking at that. So looking at the impact of oil and dispersants more on the exopolymer, the TEP and the EPS. But I don't know. There's been, you're probably aware of the literature, there's been quite a few publications that have suggested a very negative impact of dispersant. Dispersant seems to be mortality or changes in the marine population than the oil itself. Also, it appears that the presence of the dispersant changed the bacterial community, that it promoted bacteria that could feed on the dispersant. So I don't know. It's hard to say at this point.
Yeah. Well, Digna, then save your questions later.
And also about the snow. I had a long time ago, I saw in my house in Venezuela, we had a tank that we used to refresh during summer. And we noticed every time it rained, the water got very, very clear, and we saw in the bottom a lot of things laying there. And it always surprised me because it seems like the brain make whatever happens in the water to populate and go down.
Yeah.
And then when you were talking about maybe the relationship with the river, with the water river, I was thinking, oh, maybe the pH changed. And when there is a change in pH, I know that many things percolate in the water. So I don't know, I think that's very interesting.
Well, there's also high sediment load, and runoff water. clays. You know, it's like throwing clay on something, you know, then it sticks to suspended material and sinks. And so you see a lot of that too close into Mississippi River. So that's, there's actually a whole body of literature called oil mineral particle interactions, OMAs, that are separate from the marine snow activity. And that's well known near shore. So that could be what you're seeing as well. Could be a lot of things.
Well, Conjurers is just upstairs, right there. Okay. Yeah. So I'll end this morning session with an overview talk about our group on optical oceanography. So actually, this is the old picture we took maybe 3 years ago. I always told myself I should update. So without introducing everybody here individually, you can go to our web, and they each have a CV and picture, so you know them better. So basically, we have students, postdocs, research associates, and visiting scholars. And the lab is called Optical Oceanography Lab, or OOO. But I'm struggling between this and Optics and Water Lab, or OWL. Maybe you can help choose. Okay. So anyway, instead of giving you a detailed information on particular projects, this is the overview talk on what we do as scientists, engineers, and students. So the overall research goals are to understand and quantify how light, okay, this is the keyword, light, okay, optics, how light is scattered or absorbed by various materials in the water and air, and to understand how the ocean ecosystem is changing in terms of phytoplankton blooms, benthic habitats, optical water quality, and their connections with climate variability and human activities. So light is the key, and we use light. And we have several projects currently going. First, to characterize bioptical properties of coastal and inland waters. And many people are interested in this. And for that, we develop optical remote sensing algorithms and apply those algorithms to study algal blooms and river plumes. I'm going to show you a couple of examples. And from those, we characterize ecosystem connectivity, physical connectivity and biological connectivity. Then, based on all of this, okay, we build a coastal observing system, okay, in combination with the others' work. We have our own observing system I'm going to show you. And then, whenever there are some episodic events there's need, we focus on those events. So how exactly are we going to do this? Many ways. We have to go to the field, measure things, and get back things back to the lab, measure those. And we do optical modeling and algorithm development. We do remote sensing. And we combine remote sensing optics with other disciplines to address questions. And finally, don't forget, we're a university. The top number one job is education. Okay. So first, lab measurements. These are just a few examples. So we bring water back and filter them and measure particles to see how they absorb light and what color of light they absorb the most or least. Okay, filtration device, fluorometer, and spectrometer. All kinds of things. There's a few. And Jennifer Canizoro is responsible for managing all of this. Okay. Now in the field, so we measure light directly in the water. Okay. So this is one of David English's masterpieces. Okay, this is the flow system. So basically, we pump water to this system, and there are lots of sensors. You can see beam transmissometer, scatterometer, fluorometer. So those are the sensors. So as the ship goes, the water passes through this, we measure those properties continuously. And we can construct a map and use this to calibrate, validate satellites. Okay? And sometimes they don't work well if we mount this on a buoy, and within 2 weeks, barnacles grow on top of that. Yes. So that's something we have to deal with. And also, we measure light in the water. We put light profiling systems in the water. Okay? So what it does is that this is a free-falling instrument. So it gets away from the ship and falls down to the bottom. Then we pull up. So as it goes, it measures light in different colors. So by that, we know how fast light disappears in different colors. So this is $26,000. Okay? And this one is a Hyper Pro. It measures many more colors in the same way, both downwelling light, upwelling light. And this is $60,000. Okay? If you think these are expensive, you're wrong. Okay? This is one of the gliders the college was able to fund a few years ago, the Slogan Glider. The glider itself cost more than $100,000, not to mention the payloads. There's a full suite of payloads, including acoustics, CTD, optics, all kinds of sensors. You may tell this sensor measures downwelling light as the glider comes up, measures how light propagates in the water column. And this part you can see, it measures the upwelling light, okay, how light propagates to the surface. And I'm going to show the beautiful results from this glider. Okay. So altogether, I think this whole thing costs about $250,000. Okay. Very expensive. But if you think this is expensive, you're wrong again. Okay. So we also use sensors on UAVs, okay, aircrafts, autonomous, unmanned UAVs. They don't belong to us, okay? So they belong to a company, and this is NASA's Sierra. This alone, without payload, is several $1 million. And this is David English standing in the hot Florida Keys, wearing mosquito mask, a full suit. So what he did was he put sensors on land and on boat to measure things, okay, to combine with this guy's measure and to tell a story. Okay. Now, if you think these are expensive, okay, you're right. Okay. We don't always use those things, expensive instruments. This is a very old laptop, and Daniel Sensi is in Tampa Bay measuring light reflectance. Okay. We are still using it. We cannot use a newer computer because this one runs DOS to operate the system. Okay. We have not adapted yet. And Brian Barnes in the Florida Keys mount the sensors on these concrete blocks. That costs almost zero. Okay. But he needs to find better ways. Anyway, so what I showed you was we use all kinds of means to measure light, okay, in different ways. This is a cruise statistics. Almost every month, we either get samples from others. We don't necessarily go on the board. But many times we do. Okay? If you look at this, all different places. That's up to 2013. And following that, we continue this trend. So we go out frequently. So don't think we are sitting at the lab, just look at the screen. A lot of field work. So what do we do with this data? We collect a lot of data. So those are the sample data for light attenuation. So how fast light disappears. Okay, the higher the value, the faster the light disappears in the water. So with this type of water, there's a lot of colors. Every one spectra shows from one location. Okay, different color from blue to red. Okay, light disappears very fast in the blue and the red. Okay, slower in the green. So when you look at the water, it's green water. Okay. Same thing when you measure reflectance. Okay. Light is reflected most in the green bands, 550, so water is green. So those are just two examples, okay, measurement. And so this is the property we measure in the field. And in the lab, we measure the absorption of spectral light by different phytoplankton pigments. Okay? This is the total absorption, and the spectral shapes have a little bit different wiggling here. They're caused by different pigments. And because you have taxonomy already to tell the species, why bother doing this? Because this can tell you the phytoplankton groups would not touch, because we can use the optics without touching the sample. That's the hope. We're still working on this direction. Okay? So that's the measurement. Another work we do is modeling. We try to understand the light, either attenuation or reflectance. We understand what drive those shapes, magnitude. Okay, this we have to rely on optical models. And I don't need to talk about even one symbol here. This is the business we have to go through from my optical oceanography class. So every student needs to learn how to interpret this light using scattering, absorption, fluorescence, and inelastic scattering like a Raman scattering to interpret this. Okay, without understanding this, you are just doing statistics without this solid science. So this is one thing. So this is the sample result. So one is measured, one is modeled. They are perfectly aligned, so good. But we don't always have this. And sometimes they don't agree. Okay? So that's just one example. Following the modeling work, if we understand what controls light, we can do inverse modeling. So basically, if you know what's in the water, you can interpret your light. That's forward. But I tell you what the light looks like. Can you tell me what's in water and how much? That's inverse. That's even harder. Okay? And this is one of the works our postdocs did. Before the work, this is a NASA standard algorithms. This is measured chlorophyll from 1 to 100. This is from Tampa Bay. Okay? The standard NASA algorithm tells you this. So there's no correlation because the algorithms were designed for the open ocean, not for this. Okay? And Cheng Feng did a lot of work to make it look like this. Okay? So a lot of improvement. And this is one of Brian Barnes' work. So before the standard, before his work, if you want to estimate from light, estimate how fast light disappears remotely, we estimate. And this is the result. The field measurement, you can measure light disappearance. And you can estimate, you get nothing. Okay? And do this. It's very nice. So we have a lot of algorithm development work. And for example, we developed a new chlorophyll algorithm for the global ocean. Okay, that has been used by NASA as the new standard after 30 years of the old standard, since 2015. Okay? And this year, that became the NOAA standard for the global ocean. Okay? All right, thank you. So that's for the global ocean, but today is for coastal ocean anyway. So I want to give a few examples of how we apply those optics work to address some questions or problems in the real world. I'm going to talk about the oil spill monitoring, red tide harmful algal bloom, and green tide macroalgae bloom, and coastal optical water quality, such as light availability, water clarity, and chlorophyll, and so on. So first is the oil spill. And this is the first ever image, I emphasize the first, right after the spill. Can you show this blob? This is the first image on April 22nd. Look at this one. And how do we know that's the oil, that's not cloud or anything else? Because we can look at the spectra. Okay, I don't have it here. For every pixel here, you can extract the spectra, look at the spectral shape and the magnitude to tell the difference. Okay? And then from lots of images, you do statistics. And Kendra showed the statistics based on radar data from Ian McDonough. Here's the statistics based on optical data. Very similar, and we published this. And recently, one of the students, Shaojie Sun, used the same technique and developed more spectral analysis to focus on this ice-talk oil spill back in 1979. Okay? So it's a history already. What do you do if you want to study? Satellites. Okay? Fortunately, Landsat and CZCS covered this period. So he did this oil footprint and the trajectory. And the weatherbird, remember last month, we have a lot of people out there, okay, collecting sediment samples. And last year, they also collected, they used this map as a guide to determine where to go. And they found a lot of oil. And by the way, Shaoji for this work and other works was recently selected as a Gamri Scholar. Congratulations to Shaoji. Red tide. So how do we monitor red tide? There are different ways. Here, based on optics and remote sensing, red tides, they strongly absorb blue light. Okay? But these organisms are not the only one that absorb blue light. And color dissolved organic matter, which come from coastal runoff, also absorb blue light. How do you differentiate? And this is the way, From here you have a big patch of dark water because all blue light is gone. They are being absorbed. Only phytoplankton have this solar stimulated fluorescence. So every color represents the intensity of the fluorescence. Okay, if you have a lot of fluorescence, color dissolved organic matter do not fluoresce in this spectral region. So they have no signal, but phytoplankton does. So you have from this big patch, this small one is a bloom. But we cannot tell whether this bloom is due to diatoms or dinoflagellate, okay, because they all do this sort of fluorescence. And Cannizzaro developed this technique. So dinoflagellates are elongated, it's larger, and they face, in their developing state, they face less grazing power. So they scatter light less. So in other words, they have a lower backscattering efficiency. If you have same amount of diatom, same amount of dinoflagellate, the second one scatter light less. That's what it tells. So for the same amount of chlorophyll, these are dinoflagellates, these are diatoms. And based on this, we tell where is the bloom. If the bloom is this or this, we can tell better whether it's a red tide. But we did not stop there. We implement this in working with others, okay, to implement a red tide monitoring system. And the system has three basic components. Okay? This image-based component, that's every day. If you don't have clouds, you see something. Okay? And these are Bob Weisberg's surface currents. Every day they generate products. Okay? And all these are in Google Earth. If you click on one of the arrows, you can read the current speed and direction.